Hello everybody and welcome to Gravitational Fields Lesson 8. Now in the last video we just started to round off this topic, just have a look at the few little bits and bobs to do with gravitational fields. So we looked at the gravitational field strength inside a body, so inside a planet or the sun or something like that, and we had a look at escape velocity as well. Now in this lesson, which is going to be the final video of this topic, we're going to have a look at satellite motion. In other words, how satellites work, especially man-made satellites in moving around the Earth. Now in this video, when we're talking about satellites, we're mainly going to be focusing on man-made satellites. Obviously we know that the Earth has a natural satellite in the moon, but like I said, focus of this video is on man-made satellites orbiting the Earth. Now there are several types of orbit of satellites that are orbiting the Earth, and the three main types that we see are low Earth orbits, medium Earth orbits, and geostationary orbits. Now, of course, there are other types of orbit, but these are the sort of major three, and there are a couple of different subcategories of these as well, increasing the number of orbits that we see. Now, when it comes to low Earth orbits, we're talking about an altitude, a height above the Earth of anywhere between 100 and 1,000 kilometres above the surface of the Earth. Now, while that may seem quite low, especially if you've only got a height of 100 kilometres above the Earth's surface, take it into context that really the sort of maximum height that a commercial aeroplane would fly at, so the maximum cruising altitude is around about 42,000 feet, which is only really around about sort of 12 or 13 kilometres of altitude. So 100 kilometres is way above anything that at least commercially would put up. There are some weather balloons that might go higher, but again, nowhere near some of these low Earth orbits. Now, low Earth orbits can be at any angle compared to the Earth, so they can orbit above the equator, or they can orbit at any angle between the equator and the poles. Now, there is a special type of low Earth orbit, which is known as a polar orbit. And the polar orbit, as the name suggests, orbits over the poles. So if the North Pole and South Pole are there, the way that we're going to draw it, it will orbit in that kind of direction above the surface of the Earth. Now, polar orbits, again, as I said, they're a kind of a low Earth orbit, and their altitude goes anywhere from around about 200 to 1,000 kilometres. Now, polar orbits have good applications, they have special applications, and the main applications that we care about with polar orbits, they're used for monitoring weather, they're used for taking images of the Earth's surface, and then there are obviously various military applications as well, especially when it comes to reconnaissance and obviously spying and all that kind of stuff. Now, at the other extreme, we have geostationary orbits. And with geostationary orbits, the clue is in the name. Firstly, we've got the word stationary, which we obviously, hopefully by now, know what stationary means. We also have the word geo. Now, what that means is that at least relative to a certain point on the surface of the Earth. These satellites will be stationary. And we'll come on to have a look at the maths behind geostationary orbits in just a moment of time. But obviously geostationary orbits will orbit at a much greater altitude, which we'll calculate in a moment. Now, medium Earth orbits are obviously in between. So they're between low Earth orbits and the geostationary orbits. Now, of course, what it's good to know about low Earth orbits, polar orbits, medium Earth orbits, what we really need to make sure that we understand in this video is how geostationary orbits work. So, as I said on the last slide, we know that they are stationary relative to a certain point on the Earth's surface. Now, because of that, if they're stationary relative to the Earth's surface, what that means is if you look outside now, obviously during the daytime it wouldn't work that well, but at night time, depending on whether you've got a decent enough telescope and all that kind of stuff, you might be able to fix your telescope onto a certain satellite orbiting the Earth. Now, in theory, if you left that telescope set up exactly where it was and came back the next day, that satellite should still be in vision. Now, what's the point of that? Well, the point of that mainly comes down to communications. And the main type of communication is obviously satellite communication. Okay, so when we're looking at satellite TV, satellite phones, and all that kind of stuff, we'll use geostationary satellites. The other major use of a geostationary satellite is GPS. So if you've got a sat-nav in your car or anything like that, that will be logging into the GPS satellites, and that will be getting its position from GPS, which are all geostationary satellites. Now, in order for that to work, the satellite must orbit above the Earth's equator. Okay, so it will orbit directly above the equator. Now, in order to convince yourself of that, depending on where you live, maybe pop outside and have a look at some of the houses around you. And if any of them have got satellite TV, Sky TV, whatever that's going to be, we know that they're going to have a satellite dish on the side of their house. Now, with the compass, again, whether it's a proper compass or a compass on your phone or anything like that, if you just have a quick sanity check as to which direction these satellite dishes are all pointing, you'll notice they're all pointing in the same direction, and they're all going to be pointing south as well, because compared to us in the UK, those satellite dishes orbiting above the equator are all south of us. Now, finally, the key point when it comes to geostationary satellites, bearing in mind that they've got to be stationary relative to the surface of the Earth, we know that their orbital period must therefore be 1 day. We know that the Earth does one rotation in 1 day. That's basically the definition of a day anyway. But therefore, these geostationary orbits must stay in sync with us as we rotate on the Earth, and therefore they've got a time period of 1 day as well. Now, finally, just before we move on, obviously we're calling them geostationary orbits. Depending on where you look, depending on what website or what textbook you look at, you may also see them called geosynchronous orbits as well. But though there is a subtle difference between the two, but at least for the purposes of A-level, the two essentially mean the same thing. So here's your question for this video then. Calculate the altitude of a geostationary satellite and its orbital velocity. As usual, pause the video at this point, go and have a go at it and come back when you think you've got an answer. Now, in order to have a look at the altitude, what we're going to do is we're going to apply Kepler's third law. And of course, Kepler's third law as the full equation is t squared is equal to 4 pi squared over gm multiplied by r cubed. And of course, if you go back to the video where we looked at Kepler's third law, you remember me saying that this applies to anything that's orbiting another body. So it's fine for the Earth going around the Sun, it's fine for the Moon going around the Earth, and it also therefore works for man-made satellites orbiting the Earth as well. Now, of course, if we rearrange this, we're looking for r cubed is going to be gm times t squared over 4 pi squared, or in other words, r will be the cube root of all of that. Now, of course, we can start to plug some numbers in at that point. So cube root of g, we know, is 6.67 times 10 to the minus 11. Mass of the Earth, 5.98 times 10 to the 24 kilograms. And then for the time period, we'll just take 24 hours. Obviously, we need to multiply that by 60 and by 60 again. And remember to square it. And then all of that will be divided by 4 pi squared. Now for t, I know I've taken t as 24 hours. If we're doing it absolutely properly and absolutely by the book, we should take it as 23 hours, 56 minutes and 4 seconds. And again, you might want to check that to see how far out we are with any rounding, but we'll just call it 24 for now for simplicity. Now, when we do that in the calculator, what we end up with, if you put it in kilometres just to make life easy for us, we end up with 42,250 kilometres. But as usual, remember that that value, based on Kepler's third law, is from the centre of mass of the Earth, and as usual we need to then subtract the radius of the Earth to get the altitude. So the height will be 42,250 minus 6,370, which gives us a final answer for the altitude of 35,880 kilometres, so just under 36,000 kilometres above the surface of the Earth. On a new slide for the velocity then, we're going to obviously treat this as circular motion, which we know it is. So we're going to start with the equation omega is v over r, or of course we can just say v is omega r. Now we know that omega is either 2 pi over t or 2 pi f, but again we already know what t is. T is 24 hours, so we can plug that in very easily. So if we substitute that in, v is equal to, and we end up with 2 pi r over t. Start to plug some numbers in, so 2 pi multiplied. Now, but for r here, remember again it's the radius of the circle, so what we want is the distance from the centre of mass of the Earth. And therefore we want the value of 42,250 kilometres, so times 10 to the 3. And we're going to divide that by, again, the conversion from 1 day into seconds 24 by 60 by 60. Now realistically for this value here, I did keep my calculator value from the last screen in there, so again, just to make sure that we avoid any rounding issues on that. When it comes down to it then, when you do those calculations and work it all through, we end up with an answer of 3072 meters per second, or we can see that that is approximately therefore 3 kilometers per second. So to summarise then, obviously I know this has been a relatively short video, but like I said, this was just the last little bit that we needed to worry about with the gravitational fields topic. So in this one we've looked at satellites, and we looked at a couple of different types, a couple of different categories of satellite orbits around the Earth, but the main thing that we wanted to look at today, the main thing that you guys need to know about, is how geostationary satellites work. So the key points when it comes to geostationary satellites are that they orbit above the equator, that they are stationary relative to the surface of the Earth, and therefore they have an orbital period equal to 1 day, or therefore equal to 24 hours. The main uses of them therefore are for communications, okay, so we're talking about satellite television, or obviously satellite phones, and again a major one that we look at is GPS. So as I said then, that's the end of this video, and that's therefore the end of the gravitational fields topic as well. As usual, any queries, please don't hesitate to get in contact with me. Other than that, I hope you enjoyed that series of videos and you got something useful out of them, and I'll see you in a different series.